Hey everybody, so I wanted to go through this problem. This problem is actually a little weird, and I don't think there are any videos like this one. But this one is, it gives us a little bit of an idea about how to work with the probability of the type 2 error. So the type 1 error is always present when we're doing hypothesis testing. The type 1 error is the alpha value, so it's actually normally just given. Type 1 error means that we fail to reject the null hypothesis when the alternative hypothesis was actually true. So we're going to do that in this case at 9%. That being said, the alternative hypothesis is that we reject the null hypothesis when the null hypothesis was actually true. So this is a little more difficult to compute. And I fall into the problem here. I like to just say that this is the p-value. Now, a lot of times that's pretty close, it's pretty accurately close to the p-value, but that's not entirely true, and I need to be more careful than that. So I'm going to run through this computation, and I think this is the only question that asks for it. But let's do it anyway, and we'll run through the computation. Okay, so I have given you a few things here. I've said n equals 59. I have said here this should be mu. So the find the probability. So find the probability that the test is unable to conclude that a new safety equipment is effective when the mean percent reduction is actually 0.7%. So what happens here is there's really like two mu's floating around. There's another mu that is a 0, that there was no improvement. But that's going to be the null hypothesis. And what's actually happening here when we try to compute the type 2 error is that actually there was a 0.7% reduction, although we thought that there was nothing. So that's a little tricky here. There's kind of like two mu's floating around. Basically, there's this one mu that would be the null hypothesis, but we need the second one that's actually what's happening. So we're going to be testing, we would have tested about 0, but instead we know that the test result was 0.7. So that's a little confusing, more than a little, I think. I also have the sigma here that was given to me as a population mean. Okay, so the first thing I'm going to do here is I'm going to take the alpha and I'm going to convert that into a z star. So to convert the alpha into a z star, we know we use norm dot inverse, and we give it the probability. For this one, I want to be, let's see, 0.91, and a mean. Oh, and I'm going to go ahead and not compute a z star, but I'm going to compute an x star. So I'm going to tell it that the mean is 0, but the standard deviation was 9. My standard deviation here is 9, right? So that gives me what am I trying to say here? It gives me an x star of 12%. Because that's how far away from 0 the mean I would have been. This would be the critical value, that if you get more than 12%, well, you know what, guys, I didn't do the standard deviation correctly. The standard deviation has to be divided by the square root of 59, because that's actually the standard error here, computing an average. So if the change was greater than 1.57%, that's much closer to what my mu was, I would have actually found that there was some difference. Okay, so my mu that I calculated was not bigger than this critical number, right? This mu that they would have that I would have had. So I would have failed to reject the null hypothesis that I was any different from 0, but they're telling me that I was different from 0. So that's what's really tricky here, I think. Okay, so then what I want to do is I want to talk about if I had known this value, and this was now, instead of 0 being the center of my computations, I'm now going to use this 0.7 as the center of my computations and see how that differs on this guy. So what I'm going to do here is I'm going to compute a new z, let's write z here, and the new z is going to be one where this is my mu. Sorry, I always do the x bar first, right? And I'm going to use the 0.7 as my center of my computation. I'm going to divide by the standard error, which is sigma divided by the square root of the n. And I'm going to compute a z-score of 0.744. So if this guy had been my null hypothesis, and this had been my critical value, that difference would have given me this kind of z-score. And that would have been where I would have, that is the difference that I would have needed to reject the null hypothesis. So let's convert that into a probability. Norm, we need that as statist. I give it the z, and I ask it to do cumulative. True. And that bad boy right there is the probability of my error. Okay, so what's weird here is there are two null hypotheses coming at you. There's a null hypothesis that there is no difference, 0, and then there's this null hypothesis that we just like magically know this one is actually what's true. So I compute the critical value above which I would have rejected the original null hypothesis, the 0, and I ask if 0.7 is actually what's true, what's the probability that I would have been able to reject under those circumstances? And that gives me this computation of the type 2 error. So I have to know what's actually going on to compute the type 2 error. So there was some difference, 0 to 0.7, but it would have never been enough to reject the null hypothesis, or would have only rarely done it. I would have had this type 2 error 77% of the time. And this is an issue, right? Because when we set these null hypotheses are always equal. If you're really close to the value you set equal, you're not going to be able to reject the null hypothesis very often. You're not going to be able to reject the null hypothesis 77% of the time. And so really we're going to run up against a wall a whole bunch of times where we can't get the right answer. Okay guys, I know this one is hard. Give it the old college try. Remember there's like 5 extra questions in here. Hopefully I've explained how you need to do this. So you're going to take the no change. You're going to compute a critical value above which you would have gotten it. You're going to go back and do another normal distribution, now with the center at how much they actually say the reduction is, and that will give you your type 2 error. Alright, keep working hard guys. We're almost done.